All right, so we're going to do this problem here. Um, this is the steam turbine, and we're told that it is a steam turbine operating with water as the working fluid, and the inlet stream is 3 megapascals at 400 degrees C and 2 kilograms per second. What's coming out is at 3 kilopascals, so you're just told one thing about the exit state. You are told that the turbine is 92% efficient, and we'd like to know what the output power would be. So this seems like a really reasonable question. If you were designing a system, you'd kind of know what's available to you, and then the salesperson would tell you kind of the rest of this stuff. So this looks like a straightforward application of the first law to solve for or work out. So if I write the first law here, you can see I got the left-hand side, which is the control volume. And then you got the right-hand side, which is all the fluxes, the ins and outs of work and mass. So because it's a steam turbine operating steady, the whole left side will be 0. And then we don't have any heats going in or out, so we're going to assume that it's adiabatic. And so that'll get rid of these terms. And we're going to neglect the potential and kinetic energy. So really, we're going to have a pretty simple work out equals m dot times the change in 1 minus 2. So it kind of makes sense. Like the energy of the inlet stream, this is the high stuff, right? It's coming in at 3 megapascals. That's high pressure at high temperature, 400 degrees C. It's coming out at low pressure, and I imagine a lower temperature. So it makes sense that H1 is going to be big in this case, and H2 is going to be small, kind of the internal energy of the working fluid. And the difference will be the work out, assuming that we didn't lose any heat, right? So it's perfectly adiabatic. So at this point, I think we can try to fix the states. So state 1 is pretty simple. It's superheated vapor. You can just look it up at this pressure and temperature. And state 2, you don't know the enough information. You only know that it's coming out at 3 kilopascals. So what we're going to do is assume that it's isentropic. We're assuming that it's adiabatic, which we kind of already did when we got rid of all of the heat transfer. And we're going to assume it's reversible. Now, when we do that, together, this is isentropic. And in this case, that means that the inlet stream Sn is equal to S out. So here, when I solve for state 2, I'm just going to say that S2 is equal to S1 along with the 3 kilopascals that was given, and I'm going to solve for this state. This turns out to be a saturated liquid vapor mixture, so I'm going to solve for the quality. I get a quality of about 87.6%. And then from that, I can solve for the H value, H2. Notice I'm putting this S here, H2S, X2S. That's to remind us that this is the isentropic state. This is the ideal state. So I can go ahead and look these values up at these conditions and get an H2S of 2,335.7, but that's the isentropic S. And I can fix that with this 82%. I can determine what the actual work is going to be. So this is a key word here, actual. If they had said, what's the ideal work, then you would be solving for the isentropic work versus the actual work. So let's remind ourselves of what this isentropic efficiency is. For a turbine, it's work actual over work isentropic. So the work out actual over the work out isentropic. And I'm going to put a little T there for the turbine. So then I can write my H values as H1 minus H2 sub A for actual, H1 minus H2 sub S for ideal, where each one is defined as 1 minus 2 actual versus ideal. So I can use these relationships. Obviously, there's like several equations here that I've written, and so I can use them in various ways to solve various problems. In this case, I can solve for the actual work out by rearranging this to be the eta times the isentropic work if I just multiply both sides by this isentropic workout or ideal workout. So I know everything now with regard to the states, so I can just write This is the 92% efficient times the mass flux that was given times the change in entropy, and get 1649 kilowatts.